The power of artificial intelligence is to a large degree built upon statistics. And what is the common saying in statistics? It's correlation does not equate to causation. Here we have a guest on the channel for the first time, not in a direct podcast setting, but we have a special guest here who is a PhD in space physics. He is also the co-founder of two companies, Nordic Numbers and Neural Codex. So he will be explaining here what is the importance of distinguishing between correlation and causation. Why is this important when it comes to and why this is important when it comes to artificial intelligence and machine learning. So I bring the word over to Jone. Please feel free to welcome him in the comments below, and hope you all learn something here.
Hello, Stefan, and thanks for having me here, especially to talk about such an important topic as causality. Or at least I think it's important. In statistics, most have heard the mantra that correlation does not imply causation. But then we still go on to focus on correlation. Why do we do this when what we are really interested in is causation? Because causation tells us how the world is actually connected. The method of correlation was formalized by Pearson in 1890, and he was a highly influential figure, so influential that you might have heard the correlation coefficient as the Pearson coefficient, or Pearson correlation as it's often called. And he truly believed that correlation was a wider and more important concept, where causation was just a specific part of correlation. And technically, correlation is the more broad concept, but it's debatable if it's more important. And correlation really just describes how two things, it's really just a unitless number for how two things move together. And a very famous example of a correlation is, for example, that shark attacks and ice cream sales correlate very highly. The question is though, why? Surely buying ice cream doesn't lead you to having a higher probability of being attacked by a shark, or the opposite direction. What's really happening here is that during the summertime, when the temperature is hot, more people are swimming and more people are buying ice cream. So correlation can tell you that they move together, but it cannot tell you why it moves together. For that, you need causal reasoning, or causal mechanisms, like that the temperature is increasing, both of them. And this requires human thought beyond what just the data tell you. And some can probably think that, okay, but for a situation, if you have a good machine learning model and you just feed in a lot of variables, it would surely predict pretty good. And that might be the case if the data environment is stable. And with that, I mean that the new data it's supposed to predict on looks or has similar characteristics as the data the model saw in the training set. But this is generally not the case, and you can name fields like consumer behavior, the energy sector, and financial markets, where you have new trends coming and going and making a really dynamic data environment where it's really hard to, like, the new data coming in will in many cases be different than the training data. So how do we then test or how do we actually investigate causation if machine learning models and traditional statistics is not enough. Most people have probably heard about what's known as A/B testing or randomized controlled trials, which are used in medicine. And these are experiments, designed to actually get the causal effect. And for example, in an A/B testing scheme, which is often used to test new features in an application, then you randomly assign users 50-50% to the new features and to the old features. And if this random assignment is done in a way where the characteristics of the populations are fairly random, but still equivalent between the two test groups, then you can just subtract the results between each of the groups to get the causal effect. And it's the same for a controlled experiment in medicine, controlled randomized experiment. But in many cases, you cannot do a controlled experiment. It can be unethical, like experimenting on if smoking gives cancer. It's unethical to assign people to smoke. And it can also be really resource constraining or just impractical. And especially in business, it can be very impractical to have like a experiment where, let's say you have an investment fund, and then 50 funds are going to do one strategy and 50 funds are going to do another strategy. Like nobody wants to be in the control group. So you need something else. And this something else actually exists, and it's called causal inference. In causal inference, you can actually model the situation you are looking at to get the causal effect, even if you only have observational data. But this method, this method is not really widely adopted yet. And you might ask why. Some of it, in part, probably comes from these estimation methods in causal inference being very computationally expensive. And some of it comes from that if you want to answer causal questions from observational data, you need to model how the data have been generated. And this often requires domain expertise surrounding the situation you are looking at. So it's a quite resource-intensive task. However, recently, machine learning models have been able to efficiently estimate the previously expensive estimations, and large language models are also showing great promise to kind of act as a reasoning agent or a domain expert agent. And this is all in the scientific literature. So, and also in the latest years, it has come many new open source softwares for really solving causal problems. So it's becoming easier and easier. So how does this relate to business? If we can answer causal questions, we can answer things such as, how did the latest sales campaign impact revenue? And how would the revenue be impacted if we would have run an alternative campaign instead? What are the causes of subscription cancellation, for example? Or if you have many divisions in your company, how do each of these divisions contribute to the company performance? Or what are factors affecting employee turnover? How is team size, salary, and flexibility affecting workers' happiness? And it's a range of questions which really is about just understanding the connections in your business, how it works. And if you understand how things work, you can also intervene and sort of induce the results you are after. So there is a lot of value in this causal inference or causal analysis approach to businesses, especially in the environment we now have, where businesses are gathering more observational data than ever. And I also want to say, as a data scientist myself, I think that causal analysis is going to become a pivotal skill in the coming years. Thank you.
Thank you again, Jone, for joining the channel, sharing your insights, and to everyone who has been watching the video so far, thanks for watching. Be sure to like and subscribe for more videos like this. Be sure to follow and connect with Jone on LinkedIn. Help him out a bit, and yeah, share your thoughts in the comments. What you think about this topic when it comes to causation in the relation between correlation and causation, causation in terms of business applications, A/B testing, and so on. If you have any thoughts, any experience with this field, be sure to comment your thoughts down below. Or of course, if you have any questions, just be sure to shoot those in the comments below, or to a message either to me or to Jone. So I hope you all have enjoyed this video, and yeah, hope you all have enjoyed this video, and let us know what more content you would like to see more of. And yeah, other than that, I wish you all a blessed day forward, and we will see you, and I will see you in the next video.